Hello. So welcome to this week's podcast episode with starting out with quantum computing. So today we are looking at reviewing the most popular quantum computing YouTube videos. So we're switching up a little bit, and today we're going to be looking at the most popular quantum computing videos on YouTube. And so, of course, in this podcast format, I can't actually play the YouTube videos for you, but they will be linked below or in my written blog on my Substack. So feel free to check either of those out. So without further ado, let's just get into it. So the first video is by a YouTube content creator called Rillo, and he's talking about Microsoft's insane quantum chip. It's known as Majorana 1. So the video starts off and there's quite a lot of hype within this video. There's the direct call from Microsoft and this unknown employee, and then there's a sudden flight to this undisclosed location, and then we get a laboratory tour, which is amazing, to be fair. And this video managed to get a staggering 36 million views, even though it's a very short form video known as YouTube Short. So it is incredible. And Rillo is talking about Microsoft's breakthrough, which is the Majorana 1. It's the first quantum device created by Microsoft for quantum computing. It was announced earlier this year in February, and its reveal garnered equally as much anticipation as it did skepticism within the scientific community, at least. And so the reason Microsoft created the Majorana 1 was in order to establish progress on a completely different type of quantum computer, one that uses qubits known as topological qubits. So topological qubits are made out of a topological material, and what this basically means is that they are inherently resistant to errors that are usually caused by the external environment. So we hear the term decoherence a lot. And so in theory, creating a functional topological quantum computer would completely skyrocket quantum computing progress. Without errors, we could suddenly scale quantum computers to huge sizes with loads of qubits and run incredibly complex algorithms with high probabilities of success, ones capable of completely changing the fabric of the future. However, Microsoft haven't quite done this. They have created a QPU, a quantum processing unit, which is the heart of a quantum computer, but it doesn't quite show signs of being topological. Topological is a definite state of a material, and it's hard to achieve experimentally. So what they're looking for is a definite signal to confirm that they have created Majorana particles, which in turn could be used to create topological qubits. But unfortunately, with the evidence currently provided in their academic publications, it could still be said that these signals refer to other non-topological properties, such as something known as Andreev modes, which are equally plausible to exist. But nevertheless, this video does a great justice to quantum computing. We need to be excited because progress is progress. We, as the viewer, get to see inside cutting-edge laboratories, and Rillo, the YouTube content creator, does a really good job of explaining what the Majorana 1 is and what qubits are and why we should be interested in quantum computing. And Rillo goes on to explain how qubits can be innately advantageous over classical bits using the maze analogy, which is a very common analogy. So I appreciated this. Moving on to video number 2. It is called Quantum Computers Explained, The Limits of Human Technology, and it's by a YouTube content creator known as Kurzgesagt. It's an odd name to pronounce. And I quite like this video, to be honest, because there's a subtle art in being able to explain something simply, but without dissolving or removing any element of truth. And so this YouTube content creator is able to do this really well. They start with outlining transistors. These are the little Lego pieces, if you will, of a normal computer. They're little switches, and you can think of them like light switches, really. If they're in one state, the light is turned off, and if they're in another, the light is turned on. And so we can use these transistors for computing things, for operations, for calculating things, and for simulating things. And throughout history, large companies have been trying to make these transistors smaller and smaller over time. But this in itself is quite a problem. As we make transistors smaller and smaller, and as we approach the atomic scale, we enter the quantum realm, where quantum effects are much stronger. For example, electrons that flow within transistors. These electrons are usually fine when the transistors are large, but when we make the transistors small, the electrons are able to quantum tunnel outside of the transistor, causing the transistor to fail. Or another quantum effect known as inversion layer quantization, is a quantum effect that can affect the flow of electrons, and it can cause the transistor to behave differently. And that can also dominate at atomic scales. So this is a reason why it's anticipated that quantum computers that use quantum bits can outperform classical computers in certain tasks. Because with quantum computers, we don't have to worry about the quantum effects dominating, because that's exactly what we want. Quantum computers are inherently made of quantum systems. So if anything, we want to retain and amplify the quantum effects such as superposition and entanglement, as they are the precise reason as to why quantum computation is advantageous in certain cases. And towards the end, the YouTube video touches upon quite an important point about quantum computation. So even though quantum computers can calculate many things at the same time, ultimately the user of the quantum computer has to measure to get a result. And when we measure, something known as wave function collapse happens. So all of the possibilities that we were able to compute with using superposition end up collapsing, and we only get one answer out of the quantum computer. And this is an innate axiom of quantum mechanics. Quantum computing in its most basic form is completely probabilistic. It's like rolling a dice. You might get 1, you might get 6, and everything in between. So to combat this, quantum algorithms skew and increase the probability of correct measurement by cleverly manipulating qubit states with superposition and entanglement. So the way we design quantum algorithms is crucially important, as we want to increase the chances of measuring the correct result and getting the solution. And this is the core reason why quantum algorithms could be advantageous. And I think it's important to make a point here, because quantum computers aren't a god machine. So we're not going to be using them for literally every single computational task. Much like how you wouldn't take a jet to travel to the town over. You wouldn't use a quantum computer to perform normal tasks that classical computers can already do with ease. Quantum computers are best suited for very hard tasks, such as simulating quantum systems and performing certain tasks faster, such as factorizing large prime numbers. So now let's move on to video number 3. So this is by a company and I guess YouTube presence known as Wired, and the video is called Quantum Computing Expert Explains One Concept in 5 Levels of Difficulty. So this is an amazing video, because the way it works is that it guides the reader from the most simple explanation to a really complex explanation, which is kind of what this Substack aims ultimately to do. This Substack is meant to be, and this podcast therefore is meant to be simple and to help the reader understand the basics of quantum computing and the fun things about it. And ultimately, I leave a lot of the investigation and research to the reader. I leave a lot of sources. So if you're ever interested in trying to learn more about quantum computing, if I've piqued your interest in any way, there's plenty of resources here to help you kickstart that journey. But regardless, back onto the main focus. So here in this video, we have a Dr. Talia Gershon of IBM, and she is explaining quantum computing to 5 different people of different levels, from a literal child to an expert in the field. And so we start off with the 8-year-old child, and it's impressive to see Dr. Gershon attempt to explain quantum computing to an 8-year-old. And so I think explaining the quantum element was too advanced, but I thought she did a good job of giving the child the impression that computers, they speak a different language. They use ones and zeros to encode information, and they can solve complex tasks. They are very good at solving, for example, the child's homework, shall we say. So I thought that was sweet. And then moving on to the teenager, things start to become more complex. The doctor starts to talk about quantum effects such as superposition, and uses the coin flipping as an analogy for superposition. And so when you flip a coin, it could be heads, it could be tails. But what happens, let's say you spin a coin, what is the state of the coin purely in the time in which it is spinning? So not when it stops. What is the state of the coin when it's in the process of spinning? And so this is a state that is neither heads nor tails. This is a superposition state. Then we move on to the undergrad student who is a major in computer science. And although she had not specifically heard of quantum computing before, her field naturally intersects quantum computing. So there are a lot of things that are involved with computer science and quantum computing at the same time, such as quantum machine learning and hybrid quantum classical computing. These sectors are intertwined with quantum computing because we can let the quantum computer handle the parts which classical computers struggle with, yet we can allow the classical computer to optimize and tweak the quantum computer simultaneously. So by allowing for this process, it can act as a solution for solving problems that we never thought could be solved before. Where quantum computers fail, we can fill the gaps with normal computers. So this is quite a revolutionary field. So moving on to the graduate student, this is later in the video. Here the things start to get quite complex. So now we're talking about the structure of a quantum computer, how the qubits are manipulated, and how we measure quantum states. And so in the background, there's a dilution fridge, and there's a very large setup of what we could colloquially call a chandelier quantum computer. It's a superconducting quantum computer that operates in very cold temperatures. And so at least with superconducting qubits, most operations that are done on these qubits, such as measurement or such as changing the state of a qubit, etc., are done using microwaves. And so the type of microwave, the frequency, the duration of these microwave pulses can completely change what happens to these qubits. So a certain pulse might cause entanglement, whilst another might cause superposition. A certain pulse might affect qubit number 1, and another might affect qubit 10. So it's amazing to understand the physical description of how quantum computers work. And Dr. Gershon also touches upon some of the shortcomings of quantum algorithms. So some amazing quantum algorithms exist, such as Shor's algorithm, capable theoretically of factorizing numbers exponentially quicker than classical methods. But Shor's algorithm requires a large number of error-corrected qubits, the likes of which do not currently exist within quantum computers today. Then our last person to speak is the theoretical physicist with a PhD in condensed matter theory, so a true expert. And the talk that they have is fascinating. They really strike at the heart of the main limitations of quantum computers. which are errors and decoherence. So quantum computers, they can't be scaled unless if we find a way of correcting for the numerous ways in which errors can occur. So one approach might be error correction, and that kind of assumes that errors will happen, but we find a way of correcting them whilst we are doing quantum computation. But another process might be, or another approach to it might be, to design a material that's inherently resistant to errors. So this is trying to not say, okay, let's try and correct errors that we know will happen. It's more saying, let's create something where we won't have any errors in the first place. And it's nice to see in this video that these two, they aren't overhyping quantum computation and quantum computing. Yes, quantum computers have an incredible potential, but they aren't going to just miraculously solve climate change or cancer in the next 5 years. Just like many fields, there will be major obstacles, and there will also be moments of genius required to reach new heights. These things take time. And equally, there's no reason to fear the inception of these powerful and useful machines. Although something like Shor's algorithm is mathematically able to break the standard of digital encryption today, we shouldn't just believe that quantum computing will doom us all. On the contrary, unlocking these new mechanisms can bring in many advantages, such as quantum encryption, which will act to secure sensitive data in a much more effective way than the normal encryption that we currently have. So quantum computing is such an exciting field. It's so diverse. There are many, many different types of qubits and quantum computers, and there are so many interesting emerging applications of quantum computing. Quantum computers can be used for gaming, for the internet. And just the other day, I stumbled across a quantum guitar, which I didn't know could exist, thanks to a comment from a subscriber. So thank you very much. In this ever-progressing field, nobody can quite tell what the future of quantum computing holds. But I believe that we should take an optimistic look at it. It's exciting, it's revolutionary, and it is going to change the fabric of the future. All right, thank you very much. And I hope to see you on our next week's podcast. Bye-bye for now.